quick revision of some divide and conquer recurrences. And then using divide and conquer, we will design an algorithm for finding the median. How many of you have seen this? Probably seen, maybe. Okay, so if I want to find a minimum element in a sequence of list, it's easy, right? You just remember an element, run through, and you can find in about n-1 comparisons. You can find the second minimum by again doing almost the same. Remove the minimum and run through. There are better algorithms. But the question we want to find is, I want to find the median of a list of some n numbers. So median number is an element of rank so you basically write the sorted order of the list and whatever is in the middle. Yeah. So you arrange them in sorted order, pick the middle element, and that's what we mean by the median element. Yeah.
Sir, you are not audible.
Can you hear me now? Can you hear me now?
Yes, sir.
Okay. Okay, so the problem we want to look at is given a list of n elements and I want to find an element of rank n over 2. You can easily find in linear time elements at one extreme, right? I want the smallest, the second smallest, third smallest, or the largest, second largest, third largest. These things you can find in linear time. Just repeatedly find the smallest, throw it out, and so on, right? So problem we are interested in is we want to find the element which will be in the middle of the sorted list. So what kind of algorithm? How fast can you do? We are targeting a linear time algorithm, but don't worry about that. What is the best you can do? You want to find the median of a list of numbers. What is the best you can do? So one algorithm is to sort the array and pick the middle element, but you're actually doing more than what is required. But anyway, so that so you have an n log n algorithm. Okay. Sort, pick the middle. Any other? Can you think of? So you've seen presumably a good algorithm to find the second largest element. What do you do?
Make a comparison tree and then look above.
Yeah. So after you find the max, how much time you need to find the second max?
n-1 plus log n.
After you find the max, it's only about log n,
Or n.
right? So that there is an algorithm to find the second largest. If you don't know, please just go look up. It is in my practice problem sheet. That how fast can you find the second maximum, right? Instead of an n-1 and another n-2 or something like that, that's one trivial algorithm. But is there a better way to do it? And the answer is yes. After you find the max, in about log n many comparisons, you can find the second largest. And you can keep doing it somehow and find the kth smallest element. Right? So one clean algorithm is build a heap. So let's, okay, fine. Build a heap, right? How much time you need to build a heap? You can build it in linear time and keep doing, delete min, delete min, delete min, k times and you get the kth smallest element. Right? How much time overall? You can do it and do k, if you want a kth smallest element. So that will be like order n plus, yeah, for median it's still about n log n. Okay. So this was one of the questions in 1970s, whether it can actually find the median in linear time, and a bunch of people came up with a nice divide and conquer based algorithm to find a median of a list in linear time, and that's what we want to see today. So let's quickly revise some divide and conquer recurrences, right? So we will work backwards to see if I want a linear time algorithm, what kind of a recurrence relation I need to solve, right? So let's recall master theorem for solving a recurrence relation, right? So then we know what kind of a recurrence I'm after, and then we will design an algorithm appropriately. So master theorem says that if you want to solve this kind of a recurrence relation, right, you have A problems, each of size n over b, solve each one of them recursively, and then you put them together in f of n time, then what is the asymptotic complexity? So the anti of n is some constant for small n, or constant n. Then the theorem says T of n, yeah. So we will compare
n to the power
f of n and n to the power log a to the base b, right? So if both are of the same asymptotic complexity, then
log BA log n.
yeah, so then it will be fn log n. Right. Fn and theta n power log a b are same, so n power log a to the base b log n. If fn is strictly larger, or okay, if fn is smaller, so if fn is strictly smaller than n power log a to the b, then the overall solution is fn.
So if it is small,
Sorry, if fn is smaller, then it is n power log a to the base b, and is theta fn if fn is omega you also need another condition, which is that some, yeah, and there exists c less than 1 such that a times f of n by b is less than or equal to c f of n. Okay, so you want to solve a recurrence of this type where it's for small constant n, it is constant, then the asymptotic complexity of T of n is fn and n to the log a to the base b are about the same complexity, then you add a multiply by log n. If fn is strictly smaller by an epsilon quantity, then it is the larger one, and if fn is strictly larger, it is f of n, and you need some regularity condition. Okay, so this is master theorem, and let's plug in some values, get some examples, right? So, for example, T of n So what is this recurrence for which algorithm? Merge sort, right? So merge sort. A is 2, B is 2. So log A to the base B is n. This is n. And this is also n. So it falls into this category. And so you know it's order n logs, right? Suppose I have a recurrence of this form, okay, and I'm not necessarily mentioning the boundary condition, but assume that it is some constant for small values of n. Then log A to the base B here is log 7 to the base 2, which is more than n squared, so it falls into this category. No, it is here. So it will be, no, it's here, yeah. It's in this category that Fn, which is n square, is smaller than log A to the base B by an epsilon quantity. So it is theta n log 7 to the base. What is this recurrence for? Do you know what? Strasson's matrix multiplication, right? You want to multiply two n by n matrices. The naive algorithm takes n cube time. Strasson came up with this way to divide it into sub-matrices of half the dimension, and then he came up with a way to multiply two 2 by 2 matrices instead of 8 multiplication, 7 multiplications and some more additions. So that was a 7 and it gave you this right. Okay, so this is Strasson's. Okay, so let's say if it is like this. Before you even looking at the formula, can you tell me what kind of complexity this will be? You're actually plugging in here. Okay. Yeah, fine. So what is it? So what is A? What is B? A is 1. B is actually 3 by 2. So log A to the base B is 0. N power 0, so that's constant. This is also constant. So it falls into here. So you just multiply by log n. So that's theta log. Okay. Instead of 2n by 3, if you had n by 2, it's also same. Because that's also log A to the base, because this is 1, as long as this is 1. This is 1, this is 1, so you'll have, and if it's n by 2, what sort of a problem it is? T of n is t n by 2 plus theta 1. Binary search, right? And that's log n, right? Okay, so okay, I'm after a linear time algorithm for finding the median. So let's see how I get linear time in this recurrence relation. Same thing. Instead of theta 1, I have theta n here. So what does this solve to? Third case, because Fn is larger. This is constant. N to the log A to the base B is a constant, because again A is 1, whereas Fn is strictly larger by an epsilon. The epsilon is actually 1. And let's also verify that regularity condition. What is A? A is 1 here, and what do I want? This theta n, f of n. So I want n by b should be less than or equal to c times n. For a c less than 1, sure, I can pick c to be 1 by b, right? By b is like 2n over 3. B is, yeah, 3 by 2. Okay. I want this, and so pick c to be 2 by 3. So this solves to theta n. Okay. So now this is what I'm going to get hold of. So what is this recurrence saying? That in linear time, if you manage to throw away a fraction of elements, in this case 1/3 elements are thrown out and you're recursing into 2/3 of the elements, but you replace it by any fraction less than 1, right? So if I write T of n is theta n plus T alpha n for alpha less than 1, right? Instead of 2 by 3, I have some alpha n or alpha less than 1. Same story, because A is 1, whatever b, as long as b is greater than 1, then that n power log a to the base b would be constant, and this is theta n, and so you have a theta n. So this is what would dominate. So the aim of my algorithm, which I'm after, is in linear time, somehow you manage to throw away a fraction of the elements, then you can go and recurse into it, and you can recurse on the remaining fraction, and you will get a linear time. Okay. So, goal in linear time, eliminate some alpha n elements for alpha less than 1, then you can recurse on the remaining. Then this recurrence would give you a linear time. Okay. So what does that mean? Let's say I have n elements, and I am after an element which is going to occupy the middle. So let's say I call. Okay, so maybe this is. Let's call approximate median. What do I mean by approximate median? Where rank of x, that is, what is the rank? Its position in the sorted list. Is less than or equal to some 9n by 10 and greater than or equal to n by 10. Suppose I manage to find such an x in linear time, right? I really want an element whose rank is equal to exactly n by 2. That's my goal. But let me relax it and somehow. So this is a rank 9n by 10. And this is a rank n by 10. If I manage to find an element who is not very far from the median, where very far means, this is what I mean, that its rank is not very far. If I manage to find such an element in linear time, then I claim I'm done. Right? So I don't know X's exact rank. I don't know exactly where X will position, but somehow I know that it's not too much at the extreme. Then I'm done. Why? What can I do? Suppose I can find such an X in linear time. What do I do afterwards? Can I find X's exact rank? How can you find the rank of an element?
In the
Take
sort.
that away.
Hmm?
Further do the same.
So I was thinking that for the rank you will compare between that region and.
But I don't know elements in that region. Okay. So suppose I find such a rank. I find such an X, right, in linear time. Like any element, I give you an element, I want to know what is its rank. Is it not easy to find? How do I find it? What does it mean rank? In the sorted list, where will it appear, right?
So in quicksort's partition function you get position and that.
Yeah, well, how do I find X's position in the sorted list?
The element smaller than that.
Compare.
Less all
You shift them there. there
I don't even have to shift, right? I am only asking for where should it go? What is its rank?
The element smaller than this
Huh.
element plus 1.
Yeah, that's it. So just count, right? Do a scan, compare this element with everybody and find out how many are smaller than that. Then you know its position is exactly that plus 1. Right? So then, here is my algorithm, find X's rank by comparing X with all elements. Okay? So let's now generalize our problem, because I am not now necessarily looking for the median element, because in the recursive step I will be looking for some element of some rank. Okay? So let's say I want to find the k smallest. The hardest case is when k is n by 2, which is what my original goal is, but as I recurse I will keep changing k, right? So I am interested in k smallest element, and I have managed to find. So this is a big if. We'll come back to this later. But suppose I manage to find such an X in linear time, then I'm claiming that I'm done. What do? First find X's rank, compare it with all elements, right? So now I know how many are smaller than this and how many are larger than this in linear time. Okay? I am after kth smallest element, right? I'm looking for kth smallest element. So if S is k minus 1, I'm done, I'm lucky, I'm finished, right? If S is k minus 1, so if S, okay, so let's say let S be number of elements smaller than X, and L is number of elements larger than X. Let's make life simpler and assume that all elements are distinct. You don't have to worry about ties, because this conveys our algorithm better. Then if S is equal to k minus 1, return X. That's my algorithm. Done, right? If S happens to be k minus 1, I am after the kth smallest element. Done. If S is more than, if S is greater than or equal to k, then where is kth smallest element? In the left side, right? Recurse. So let's call this set as S and L, and the size is S and L, right? Then recurse on S, else recurse on. That's my algorithm. Okay? But what do I mean by recurse on S? in capital S, I look for kth smallest element. But when I recurse on L, which element do I look for? Not kth smallest element. Right? When do I recurse? If S is smaller than K, let's say S is 10. K minus that ranked element, I look for it. So the K changes, but now I recurse here. This is my entire algorithm. Okay? Now let's say how much time it takes, right? This is my big assumption. I managed to find that X, that's order n time. After that, how much time does this take? Linear time. I'm comparing X with everybody. Now my recursion is T of n would be order n plus either I recurse in capital S or capital L, but what do I know about the property of X? It's at least, so whatever, suppose I recurse on the larger side, right? Then I know that at least these elements are gone. Because X's rank is in this range. The worst case, suppose X's rank is here and I'm recursing on anything bigger than X, then it's at most 9n over 10 elements left. If I am recursing on left, then I know that the worst case that X's rank can be this and I'm recursing that. So what would be this? T of 9n by 10. And from this thing, you have a linear time. So now, clear? Yeah? So now all I'm left to do is to find somehow, okay, don't bother about this exact median, but something approximate median, meaning something actually whose rank is not too much to the extreme, right? At least some fraction is this side, some fraction is that side. If I manage to find such an X, and I'll scan and find its exact rank, then it tells me which side to recurse, and I recurse, and because of this recurrence relation, I'm done. Okay? So the goal now is to find such an X. Okay. Now, yeah, so suppose I manage to find, let's play this game, right? Suppose I pick a random X. Okay? So what do? I have these n elements. I toss a random number coin between 1 and n, and whatever number it comes, I go to that location and pick that. Okay? Some random element. Now, what is the probability that it will be in this range? What is the probability that it will satisfy the X I am picking? Because X has equal probability of any of the n ranks, right? So what is the probability that X will be in this range?
Minus 1 over the size. 8 by 10.
So 8 by 10.
8n by 10, 8 by 10, exactly, 4 by 5. Very high probability, 4 by 5 probability that I would actually throw away a fraction of elements, right? So this is a very simple, like a quick sort variation, which is, let me now erase this. So here is a randomized algorithm. Quick select, pick a random X, find X's rank by comparing with all other elements. Let S be this, L be this, and recurse. This algorithm, for example, we just made a very quick, estimation that it actually will satisfy this with very high probability. That in particular, the recursive portion will be actually a fraction of elements, and then you have a linear time algorithm. Okay? But let's talk about worst case. What can it be the worst case? So what I'll write is, this is a version of quick sort for median finding. expected order n time. Okay, the quick estimation we did is not actually a rigorous analysis for the algorithm, but it's just an intuition which says that with very high probability, because there are lots of ranks in this range, you are going to pick one in that range, and then once you pick that range, you end up throwing a fraction of the elements, and when you recurse, you will be fine, you get a linear time. But what is its worst case? So worst case, what can happen?
We pick either maximum or minimum.
Yeah, if x happens to be maximum or a minimum, so worst case, let's see the running time, you have to do, how much time you do here to compare x with everybody. That's like n minus 1 comparisons. Then you are left with a big, either capital S or capital L, doesn't matter, but maybe it has everything pretty much, right? Because you pick the maximum or minimum, so it's like T of n minus 1. This, what does it solve to?
N square.
This is an n squared. So here is a simple randomized algorithm. You just pick a random element, partition. What is the difference between quicksort and this?
In quicksort, we actually move the elements.
So you can move it, but that's not the real difference. What is the difference? I mean, if it's not too much difference, then it should be n log n. Why is it linear, right? Yeah. What do you do here in quicksort? After you've done your partitioning, what do you do?
He recurs on bottom.
Recurs on both sides.
Okay, yeah.
What are we doing here?
Because only one share.
We are only recursing on one side, right? That's a big difference. Because my element median, from S and L, I know where my element I'm after, this side or that side. I know precisely that, and I go and recurse only in that portion. Okay, so it is, I mean, intuitively, if you think of quicksort as, n minus 1 plus T of n by 2 plus T of n by 2, that's like a 2 Tn by 2 plus n minus 1, whereas quick select will be like this. Okay, and this is something like this, so it's ordered. So you're doing only recursing on one side. Okay? So, but this is not a rigorous analysis. We'll probably analyze this later. Right? Or you can think about it. I mean, I don't want you to go home thinking that little first step argument we said, oh, with very high probability you throw away a fraction of the elements. From that step to conclude that the expected time is linear time requires some calculations. Okay? Not very hard, very similar to quicksort analysis, you can work it out. But, so, net, we have a simple randomized algorithm which has a linear time expected, where expectation is over all possible choices of the pivots you are picking. But now we are back to the game of doing it in worst case. Okay? So we really want in the worst case somehow close to this, and we want to throw away a fraction of the elements. Okay? So the algorithm actually is like 4 steps. If I just describe the algorithm, you're not going to understand why those steps are. I'm sort of building it bottom up to see, reverse engineer and see how they got the algorithm. So for worst case, first I'm going to generalize this recurrence a little bit, right? So suppose I have, so back to worst case, right? This worst case is n squared. Suppose I look at the recurrence relation where T of n, some T of alpha 1 n plus T of alpha 2 n plus O n, where, see,
Plus alpha 2 is less than 1.
yeah, exactly. Here we really wanted alpha to be less than 1, then only we can guarantee linear time, right? Because if alpha equal to n, then it's bad, hence it could be n squared. Alpha was strictly less than 1, then you had some sort of a geometric series which resulted in less than 1. So if where alpha 1 plus alpha 2 is less than 1, then also then you have a linear term. Okay? You can actually prove this by induction. So we let's say this is some dn or some cn. So I now assume true for smaller cases, which we, depending on the boundary conditions, you can verify. Then what is it you want? T of n is T of alpha 1n plus T of alpha 2n plus Cn, which, so let's assume that claim is some d times n, right? I want to give a linear upper bound. Let's assume T of n is at most some d times n. Then by induction hypothesis, alpha 1 is strictly less than 1. So T of alpha 1n is d times alpha 1n plus d times alpha 2n plus Cn. So this is equal to n into d into alpha 1 plus alpha 2 plus C. Right? And I want this to be less than or equal to what? dn, right? This is my claim. T of n is less than or equal to dn is what I want. So I wrote the recurrence relation, used the induction hypothesis for these two terms, plugged in all that, and I want this to be n times n. Yeah. When does this happen? What do we want? D times alpha 1 plus alpha 2 plus C, I want this to be less than or equal to 1. So, less than or equal to D. This is what I want. D is my choice. Okay, C is given in the equation. So I want to show that there exists a D I can choose such that this happens. So how do I choose this D? I want D should be greater than or equal to C by 1 minus alpha 1 plus alpha. Since alpha 1 plus alpha 2 is strictly less than 1, 1 minus alpha 1 plus alpha 2 is certain small epsilon constant, they can take that. As long as I choose D to be greater than or equal to this C by that little difference, this is satisfied and I have a linear. This is why it's important that it's strictly less than 1. Okay, so now I am going to come up with a divide and conquer algorithm whose recurrence will be of this type, and then that will give you a linear time out. Okay, so this algorithm is attributed to yeah, Bloom, Floyd, Pratt, Rivest, and Tarjan. Okay, this is actually 1973. Almost all of them have won Turing Award, not for this work, but for different kinds of work. Okay, so it required so many famous people to get together and design this algorithm. Okay. Okay. So step 1. Divide input into blocks of size 5. what is the situation? I have list of size n. I divide it into blocks of size 5. N may not be a multiple of 5, just add some large number of elements. Sorry, whatever, make it a multiple of 5 by adding some elements which are larger than all elements in the list. Okay, some dummy elements. So this is just some technicality. It's because 5 is an odd number, and various reasons it's convenient to just divide it into blocks of size n. Okay, when is not a multiple of 5, you may want to add, let's say, some 4 new elements. Because when is 1 mod 5, you add 4 new elements, suppose all the 4 are bigger than anything on this list. That's something you can do in linear time. So, divide input into blocks of size 5 and find the median of each block, right? So what is this? We somehow sort, do whatever, it doesn't matter. We want to find the median of each of these blocks. Step 2, find the median of the medians. Let's call this X. This X is my approximate median, I claim. Okay, how do I find the median of the median? The recursive. Okay, and after that, it's the same old thing. Compare X with all elements. And find S, L, little s, little l. All elements smaller than X, larger than X, and that sizes. I erase that last step, and that's exactly if x is equal to k minus 1, return x. Else if s is greater than or equal to k, then find k smallest in s. Right, so this algorithm, let's say find k in my entire list L. Else, find in the larger elements k minus s, which is plus x, right? So
this rank
rank of x is s minus 1 because s is the number of elements smaller than that. So rank of x is s, right? Yeah. So you just subtract.
is plus 1 is the number of elements.
Yeah, right, exactly.
S plus 1
So it's k minus s plus 1. That's it, right? This is the whole algorithm. Somehow we divide into blocks of size 5 and then take the medians, find the median of the medians recursively, and that x is my approximate median I was using for my quick select algorithm. So after that, compare x with all elements, and then depending on which side, whatever the sizes of these elements, recurs in appropriate portion, right? Now let's analyze the running time of this algorithm. Clearly it will find the kth smallest, right? There is no problem with correctness because we managed to find some x, compared it, and then figured out the element I am after is in this side or that side, and I go and appropriately recurse there. Okay, so how much time you spend in step 1? We divide it into blocks of size 5. There are no comparisons involved there. And then we are finding the median of each block. In constant time, there is only 5, right? So even if you do all possible comparisons, that's like 10 comparisons. If I choose to, right? I mean, you don't have to do, there are faster algorithms, but even if I do 10 into n by 5, that's like 2n comparisons. Okay? So really, even if you use a bad algorithm to find the median in each block, it's at most 2n comparisons. How much time for step 2?
T of A over 5.
Right, because you're finding it recursively, right? Good thing about recursion is you just go T of whatever number of elements. Totally there are, we divide it into so it's T of n over 5, right? Ceiling n over 5 more precisely. So this is T of n over 5. And step 3, all you're doing is comparing x with all other elements. So that's n minus 1 comparisons. So the bulk of the care, why did you do all this median of medians and so on, is to argue that we have thrown away a fraction of elements. So how many elements in the worst case are left you are recursing, right? Can you how approximate this approximate median x is? Once you figure that out, then you can plug it into the recursion again, and then this is all fine, right? So let's. So x, which I find, is the median of the medians, right? So you can clearly, how many elements are definitely smaller than x, how many elements are definitely larger than x? Right? Number of elements larger than x is greater than or equal to what? X is a median of n over 5 elements. So at least half of them are bigger than that. What is that? N by 10. At least n over 10 are bigger than it. But also each of this is a median of 5 elements. So each one has some 2 more elements bigger than that. Right? So how many can you say this? Yeah, so those elements and 2 more, right? So how many? 3 into n by 10, right? Because for half the elements are bigger than that. So let's say, this is the guy bigger than this may be a bigger one, this may be bigger, because I'm not really partitioning it, right? But for each one, this is, I found the median, so that means about 2 more elements bigger than that. So they will also be bigger than x. The element smaller than this guy, I don't know its relationship with x. But I know that anything bigger than that will be bigger than x. So there will be 3 into n over 10 elements larger than x. By the same token, number of elements smaller than x same thing. Because it's a median of n over 5 elements, at least n over 10 elements are smaller than that. For each one, there are 2 others smaller than that. So it will also be greater than 3. There may be more others that come in. Right? So, what does this mean? In this list, if you look at the rank of x, at least 3n over 10 elements are bigger than x, and at least 3n over 10 elements are smaller than x, so x is in this range, right? So when I compare with x and partition and then recurs on one portion, if I recurs on this portion, these guys are out, and if I recurs on that portion, if I recurs on larger than x, this 3n by 10 elements are out. So how much do I recurse here now? What is the running time? Yeah.
7 by 10.
7n by 10. That's what will remain at most, right? You may be lucky and even smaller, but this is. Is that clear? This is the critical step of why we are doing median of medians, taking the median of 5 and partitioning and all that. So now let's write the whole recurrence. It's T of n is some order n steps, so some 2n here and n here, about 3n. Plus T of n by 5 plus T of 7n by 2. Okay? So there is an alpha 1 and alpha 2. What is its sum? 9 by 10. Strictly less than 1. So it's linear. Okay? So it's a very clever use of divide and conquer, and the way to really see it is from the recurrence side, right? What sort of a running time, what sort of a recurrence I want, and then we craft it and cleverly remove and get that kind of a recurrence, right? So now you should ask the question, why blocks of 5? So okay. So what blocks would you want? Let's try, plug it in and see. So odd number is good, right? Because then you don't have to deal with this median being, what is it? So let's say, suppose I do median of 3. Okay? If we do median of 3, no, who says it's 3 by 10? We don't know that.
7 by 10.
Why 7 by 10? We don't know. You have to do that calculation.
Okay, 7.
You have to do the calculation, right?
N by 3 will be there.
So,
Question,
let me write somewhere. What can I erase, right? So, okay. So you have seen this picture. So if I do blocks of 3, then you will have T of n is some order n for finding the medians here, comparing it here, and so on. Plus, yes, finding the median would have T n by 3. Now let's look at this number. What happens?
N by 6.
Two.
N by 3.
2n by 6, right? So this will be like n by 3. So what will be left remaining? Not less than 1.
Therefore, n square.
No, not n
Oh,
square.
sorry.
It will be n log n.
N log n.
Okay? Because this plus this is equal to 1. If you do blocks of 7, what will happen to this number?
4n by 14.
4n by 14. So it will be 11n by 14. This is okay. Right? Anything actually greater than 5 is fine, but the constants, it starts blowing up because we absorbed a lot of things here. Now you're finding median of blocks of 7, and so you can work it out, but now you see why they chose 5 and not 3 and various reasons. Okay, so that's a very clever, very nice application of divide and conquer, and now you know that you can actually find the median in linear time. So now there's been a lot of work on this afterwards in trying to improve the constant in the front. Okay, how fast you can so for example, current best algorithm for median takes some 3 minus epsilon some n comparisons, and there is a lower bound. We'll get to lower bound sometime later, and we'll see some lower bound of y, not so much to n, but at least, yeah, 1.5 n or something is required. Okay, so my point was to just quickly, refresh your memory on the master theorem and give you one nice, clever application of divide and conquer for finding the median. Let's do another example, another non-trivial example. There's lots of time. Okay, fine. So any questions on this? What?
Okay, so why can we not do it in less than O n? I mean theta n. Something or something. I need an argument for.
Okay. So the question is, why do we even need? Can you find the median in log n time? Root n time? Forget median. Can you find the minimum in root n time? Can somebody give an argument for? Okay, I mean we will get to this when we talk about lower bound. So can you forget even root n? Can you find the median in even less than n minus 1 comparisons? Good. Now that you asked, let's. Actually, let me indulge into it. It's a good. So, when you ask the question, can we find even minimum of n elements in less than n minus 1 comparison? Minimum or maximum, right? How do you even argue this? Right? How do you even prove this?
Something like path in a tree, like.
No, so you could just comparison, the meaning of comparison, if we have to compare with all those elements, there are n minus 1 elements, and to compare all
There are n elements, right?
there, okay, there are n elements,
In worst case, like you may.
So clearly, okay, it's very easy to say you can't do it in root n, right? Why? Because I have to even touch every element, right? If you even don't even consider some element, I mean, that guy can be the minimum, that can be the median for all you care. So that would be an argument you can't do little over n, right? But touching you can still do with n by 2 comparisons, right? So how do you argue such a thing? So let's turn around and let's do the following. So there is this notion of adversary argument. Okay, you have seen this decision tree argument to show sorting requires n log n comparison, right? We will get to that later. So let's ask this question for the binary search thing, right? So suppose I think of a number between 1 and n, and you have to ask me, you have to find that number by asking me yes or no questions. So how many questions do you need? Hmm? 1 and n. I think of a number.
So log n.
Log n many questions, right?
Yeah.
What's up?
No, but as Jan said, like before knowing the rules, like I can ask.
No, I said
what is
yes or
the
no
number?
question. Yes or no question.
Okay.
You have to ask me questions where I will answer only yes or no. And how many questions you will need? Well, you can find out in log n many questions. Basically, do binary search. Is it less than n by 2? It's greater than n by 2, and you will pin me down and find in log n many questions, right? Now, let's turn the game towards me and say, suppose I want to force you to make a lot of questions, right? That's what the adversary is doing. Okay? So then what number should I think of? I'm thinking of a number between 1 and n. You are a completely arbitrary algorithm, right? You are not a binary search algorithm. I have no idea what algorithm you are. You are going to ask me yes or no questions to guess the number. So what kind of number should I think of so that I can force you to ask a lot of questions?
Don't
Just
think
like
about
any
it.
number.
Don't
Huh?
think
You
about
will
it.
not think of it.
Exactly, right? So the answer is do not think of any number, because the moment suppose I think of 73, and if you are as an algorithm, you will somehow by magically you ask me, is it 73? I have to give it, right? And in one comparison. So if I want to really force you to ask a lot of questions, so the strategy is I will not think of that number, right? I will not think at all. So now, but I have to answer your question, right? You come and ask me, is it bigger than 53 or something like that? I have to answer it. How do I answer it?
You choose the bigger interval.
Choose the bigger interval. So this is actually called the adversary strategy. So I think of a number between 1 and n. And your questions are yes or no questions. So you don't know. You might even ask, is it prime? Is it composite? Is it divisible by 27? Whatever, right? So what do? If I say yes, I rule out some numbers. If I say no, I rule out some numbers. Wherever I rule out fewer numbers, I will answer accordingly. And then I'll remember that what I gave the answer, because finally I have to tell you a number what I thought of, and it has to be consistent with whatever I thought of, right? So I choose, so I only talk of strategy, which is choose the bigger interval. Which means that suppose I am looking for 1 to 100, by luck, suppose I thought of 23, and you are asking me, is it less than 30? I will change my number, right? Which means basically I won't think of a number. If you ask me, is it less than 30, I will say no. And then immediately I will remember, oh, I have given no, so I have to actually produce a number in the range 30 to 100, back of my mind. So, I have given myself a bigger range. Now you can actually convert binary search recurrence into a lower bound argument, right? So now how many questions do you have to ask? Because in one question, it will be greater than or equal to. In one question, you are left to deal with at least half the range. Because that's the way I have answered. So this is at least log n. So that shows that log n is sort of optimal, right? That's the kind of thing we want to do. I want to show that n minus 1 is kind of optimal by an adversary argument, right? So you can think of, I have a list of n numbers, and you as an algorithm is making comparisons. And I have to answer the comparisons. And how do I answer comparisons to make you take a lot of comparisons? Okay. So in the case of min, it turns out the adversary doesn't even have to do much. It's very simple adversary. You can just arbitrarily answer. Okay. You can actually fix. So in this case, I should not fix a number. You all told me, right? In this case, I even fix a set of numbers and I answer accordingly, right? What I'll do is I'll draw a graph. So whenever you ask A1 less than A2, I will say A1 is less than A2, and I will draw a graph to just sort of indicate that I have told you that A1 is less than A2. And you're asking me a lot of questions, and I just keep drawing. I answer appropriately and draw this whole graph, right? You made various kinds of comparisons. So I maybe you ask this. So I draw this graph. And suppose you made less than n minus 1 comparisons. Then what can you say about this graph?
N minus 1 edges.
Less than n minus 1 edges, right? You have a graph on n vertices, less than n minus 1 edges, so the graph is not connected. The graph is not connected, right? So because tree is minimally connected and it has n minus 1 edges, if you had less than n minus 1 edges, it may even have cycles and so on, but clearly the graph is not connected. That means at least it has some other component. The algorithm has not learned any relationship between these two values, these two components, right? It has not learned anything. Whether anything here is because it's not connected. No such comparisons have been made, right? Now I'll watch the algorithm and it's going to say, it will say this is the minimum element. Let's say it actually made less than n minus 1 comparison. It gave the answer saying this is minimum. I'll say no, you are wrong. I'll pick the smallest from this component and I'll say this is actually the minimum, and I will be right because the way I have been giving comparisons outcome, there is no way for you, because you did not learn anything between these two components. So I am absolutely free to choose. So I will produce this input. This is the input I had in mind, where this is smaller and it's consistent with all the answers I gave, and you're wrong. Okay. So formally what did we actually argue, right? Now let's just see, what does it mean by you can solve a problem in certain f of n time. Right? You can sort in n log n time, right? What does it mean? Can you tell me in, right? Okay, so problem P. For example, you want to think, you can think of sorting, can be solved in f of n time. What does this mean? Can you just say it in logical statement? Right? You say, oh, you can solve sorting in n log n time. What does it mean?
You require that many comparison at least.
Not at least. This is an upper bound statement.
By n log n sequences of operations that you do, you should be solving the problem.
Given a sequence, after
I want some logical quantifiers coming in. Okay? Then
For all instance.
For all instance, okay. For all instance of size n.
There exists a path which provides the solution, or there exists a sequence of operations.
There exists a sequence of comparisons.
Yes.
No, you are. How? I'm just, so let's say in English, what is it? So I ask you, oh, do you know how fast you can sort, and you say n log n time. What would be your justification? What would we say?
So for instances of size n, you cannot have a sorting which is less.
No, this is an upper bound statement.
Okay, upper bound.
So this is how I say. There exists an algorithm, right? In this case, merge sort. What does it mean by I can sort in n log n? Oh, there is merge sort, which you give any instance of size n. A will solve P in at most f of n. That's all if you give any list of size n, it will actually sort in order n log n. Now tell me the negation of this statement.
For
Right?
all algorithms.
So let me write this. Okay, so this is fine, right? Now I want to write problem P cannot be solved in f of n. How do you write this? Yeah.
For all,
For all algorithm,
there exists an instance of size n of A which will solve
there exists an input of size n
which will to solve P in K
for which
greater than for of size n for which there will exist an instance of size of problem P which will take greater than f n.
which will take, who takes?
Achha, for every algorithm.
For every algorithm.
No, so for that instance of the problem.
It will force algorithm.
For every algorithm, there is a bad input
There is a value.
for that algorithm. For every algorithm, there exists an input for which A will take that's what it is, right? Now, yeah, so this is what it means by cannot be solved. So let's, what did we do with the adversary argument? By saying that the binary search will take, I mean, you have to take at least log n. What did we do? For every algorithm, that means you are the algorithm. You are asking me questions. For your sequence of questions, I will produce the input. I am giving you this bad input, right? I look at your algorithm and then decide on the input. Remember, the quantifier is in this order. There is no one input for every algorithm. You give me this algorithm, I will produce the bad worst case input for it. You change the algorithm, I will give you another worst case input. So you ask me a sequence of questions, that's your you as an algorithm. I as an adversary produce the worst case input on which you will take at least n log n. Yeah?
Sir, the connection is too weak, so we are not able to get along.
Yeah, I know. You lost for about a second. I did. You
Not
did.
for a second, like it's going and coming back for about 10 minutes.
Okay, so what?
10 minutes we are not getting the thing.
Okay, but is it okay now?
No, sir, we can't have a video properly.
Okay. Okay, so I am actually indulging in. Okay, we lost them. So in the case of binary search, this is exactly that. How did I generate the input, the bad input? I followed his strategy. Always choose the larger interval. I followed that, and that's how finally I got an input. You asked me one question, I gave that input for which I have to ask log n. How did I generate the bad input for this min-max algorithm? I just answered happily and found, finally you stopped and I found the connected components, and my input is, oh, this is smaller than this. That is my input for which this algorithm, so another way to say is for which A will take greater than or equal to fn time, or if A takes less than fn time, A will be wrong. Right? Because you stopped with n-1 comparison and you said this is the smallest, you are wrong because I have produced that input for which you are saying this is smaller.
Okay, so there is another thing over here. So you are restricted by the techniques you are using.
Yeah.
Comparisons then.
Exactly.
So
True. Yeah, whatever you can. Yeah. So I was just talking about adversary arguments to show lower bounds. We will actually talk about them later sometime. So anyway, so don't worry about it. So the point is that what adversary argument does is, for every algorithm, it provides a bad input to prove. So this is one way of proving lower bound of algorithms, right? You watch the algorithm and say, if it takes less than this, I as an adversary can come with a bad input for which that algorithm will be wrong. So in particular, if you have a median algorithm which takes root n time, I'll watch all the root n comparisons you made, I will answer them, and then I'll say, oh, you haven't actually learnt enough about the remaining elements, that I will pick the elements in a way that you will be wrong. Okay, so, and you can use this to actually show that the min and the max will take 3n by 2 comparison. Second max will take n minus 1 plus log n comparisons and so on. Okay. So I'll just lead towards what is it next I'm going to do, and then we'll stop. So next thing I want to do is, using divide and conquer, I want to give a good algorithm for multiplying two polynomials. Multiplying two n degree polynomials. So these are polynomials in one variables. So let's look at ax is a0 plus a1x plus a2x squared plus a minus 1 x squared a minus 1, and bx is b0 plus and I want to compute ax times bx. What would be the naive algorithm? How much time does it take? So the product has degree 2n minus 2, right? And if I want to find out the coefficient of, let's say, x power j in the product, how do I get x power j? A0 bj plus a1 bj minus 1 plus a2 bj minus 2 blah 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 dot, right? Something like j terms. Yeah. So some j terms I have to multiply to get my j plus 1 terms. Okay. So totally, if I want to compute every coefficient, how much time will it take? One plus 2 plus 3 plus up to n square, right?
Yeah.
It's clearly an n square algorithm. Now I want to design an n log n algorithm for this problem. Okay. This is again very fundamental, right? Because suppose I put x is equal to 2. Okay. So what is a of 2? It is actually, think of a0, a1, a2, an minus 1 as a binary representation of a number. Then I'm just actually multiplying two n-bit numbers, right? Because that number is a0 plus a1 into 2 plus a2 into 2 square and so on. Similarly b0. So this actually is a generalization of multiplying two n-bit numbers, and so if you can do it faster, it's very useful for a lot of applications, right? So how do we do this multiplication? Well, we are going to look at these polynomials in a different form. And that is called point value form. So suppose, I have some points, some values x0, x1, x2, x2n minus 2. So 2n minus 1 values, and compute, so and let yi equal to a of xi so then I will represent my polynomial a as y0, y1 to y2n minus 2 and b as z0, z1 to z2. So what is it what I'm saying? All I'm saying is, if I want to know what the coefficients are, if I know the polynomial's value on n values, n different values on which I have computed the polynomial, then I can compute the coefficients, can I not? Right? Solving some simultaneous equations, the n equations. Suppose I'm just saying, instead of this coefficient representation, I don't give you the coefficients, but I tell you the value of the polynomial on n different points, x0, x1, x2, xn minus 1. Then you write down n different polynomials, n different equations on ai's, solve them, and you get the a0, a1, a2 coefficient. So this is an equivalent representation. Now I'm not storing n different because the product has degree 2n, roughly 2n. So I'm actually storing the polynomial on some 2n many points. Similarly, I store the polynomial on 2n many points. So this is an equivalent representation of the polynomial. Instead of the coefficients, I just store the value of the polynomial on many points. As many points as I need to uniquely determine the polynomial, I may actually store it even in more number of points. Now, in this form, if I want to compute ax into bx, what should I do? The product polynomial. So that the product AB polynomial, now my polynomials are not stored using coefficients, but stored using these fixed points, the value of the polynomial on these fixed points. So what do I really care? I care about AB of x0, AB, the product polynomial on x1, and AB of x2n minus 2. I really want the polynomial, product polynomial on x0. Can I find it easily? y0 into z0, right? It's a of x0 into b of x0. So just pointwise multiply them. In linear time, I can compute the polynomial product, right? So we move from coefficient representation to this point value representation. If I have stored the value of the polynomial on so many different points, if that's the way I represent my polynomial, then the product is linear time. Whereas here the product is n squared. Okay? So now our goal to get to n log n algorithm is that you are given polynomials here, evaluate them in these points, both of them, compute the product, pointwise product in linear time, and go back and get the appropriate coefficients. Okay? Now, but if I am here, I can do it in linear time. If I am here, I can do n square time. Going from here to here and then going back will take a lot of time. Okay? How do I avoid doing this, n square step? And the way we avoid this, use the fact that this is my choice. The set of points on which I am evaluating and keeping the polynomial is my choice. Any set of points, as long as they are distinct, I'll be able to get back the coefficients. So choose the points in a way that the evaluation and inversions are easy. Then we can do the whole thing faster. Okay? And in particular, we will use complex roots of unity as the set of points, and then we will argue that then we can, given coefficients form polynomial, you can go from here and evaluate on the complex roots of unity in n log n time. Once you have this, you can compute the product in linear time, and then we can go back and invert to the coefficients in n log n time, as long as this set of points are complex roots of unity. Okay? And what is the special property which makes the whole thing work? What kind of divide and conquer algorithm we get? We'll see all of it